Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into the world of self-adapting language models, which is, a hot topic right now. It's more than just chatbots, right? We're talking about AI that truly understands and can evolve.
Exactly. And I think it's a crucial stepping stone towards artificial general intelligence, AGI. We've seen these language models get incredibly powerful with just scale and deep learning, but adapting to new situations, that's where the real magic happens. That's where AGI emerges.
I'm not entirely convinced that deep learning alone is the answer, though. It's good at pattern recognition, sure, but true intelligence requires more than that, right? It needs reasoning, understanding, which is where I think neuro-symbolic approaches have a real edge.
I agree, to some extent. Deep learning is impressive, but it feels like brute force sometimes. I think we're going to need algorithms that are better at dealing with spatiotemporal information, translating between different coordinate representations. The world isn't just text and images, it's dynamic. It's about relationships in space and time.
That's a great point, spatiotemporal understanding. Think about how humans learn. We constantly integrate information from different senses, right? We see something, we hear something, we feel something, and we put it all together in a cohesive understanding of our environment. Current AI is often siloed, just focusing on one modality at a time.
But I think the recent progress in multimodal models shows that deep learning can handle that integration. We're seeing models that can generate images from text or answer questions about videos. It's not perfect, but it's a clear trend.
Yes, and it's still relying on huge data sets and massive computational power. It's learning correlations, not necessarily understanding causality. If you change the context even slightly, those models can break down pretty quickly. A neuro-symbolic approach could, for example, use a neural network to extract objects and relationships from an image, and then use symbolic reasoning to draw inferences about the scene. It is like a combination of what you guys said.
Exactly. It needs to be able to reason about, if I move this object here, what will happen? Current models can't really do that in a generalizable way. They might be able to predict the outcome in a specific scenario they've seen before, but not in novel situations. It's like they haven't really learned physics. They've just memorized a bunch of examples.
It's almost like we need to give them an intuitive physics engine, right? Something that allows them to simulate the world and make predictions based on underlying principles, not just statistical associations. That's where I think understanding how the human brain represents space and time could be really helpful. The hippocampus, for example, is crucial for spatial memory and navigation. Can we draw inspiration from those biological mechanisms to build more robust AI models?
There's some interesting work on differentiable physics simulators. These simulators allow you to train neural networks to predict the behavior of physical systems. The nice thing is that it allows the model to learn the underlying physics rather than just memorizing examples. It's a more data-efficient approach.
Okay, but even with differentiable physics, it's still relying on predefined physics engines. What about situations where the physics are unknown or complex? That's where I think a neuro-symbolic approach could really shine. You could use a neural network to learn the underlying relationships and then use symbolic reasoning to formalize those relationships into rules.
Yes, that's what I'm getting at. The algorithm needs to be able to abstract away the specific details and reason about the underlying principles. And that requires a way to translate between different representations of the same information. For example, you might represent the position of an object in Cartesian coordinates or polar coordinates. A truly intelligent system should be able to switch between these representations seamlessly and understand how they relate to each other.
That translation aspect is huge. It's like we use different coordinate systems all the time without even thinking about it. If someone tells us to go 3 blocks north and 2 blocks east, we immediately translate that into a spatial plan. AI struggles with that kind of abstract reasoning.
Well, think about large language models. They're essentially doing translation, right? Translating from one language to another or from text to code. It's all about mapping between different symbolic representations. So, in a way, they are already doing this translation, just not in a spatiotemporal context.
But it's a different kind of translation, right? It's statistical translation based on co-occurrence patterns in the data. It's not understanding the underlying meaning or the underlying relationships between the concepts. It's more like memorizing a phrasebook than actually knowing the language.
Exactly. It's not compositionality. You can't take the individual components and combine them in novel ways to create new meanings. And that's crucial for spatiotemporal reasoning. You need to be able to take individual actions and combine them to achieve a goal, even if you've never seen that specific sequence of actions before.
So how do we get there? How do we build AI that can truly understand and reason about the world in a spatiotemporal way? It feels like we're still missing a key ingredient.
I think it comes down to better architectures and more data. We need to design neural networks that are specifically designed for spatiotemporal reasoning, and we need to train them on massive datasets of real-world interactions. The reasoning language model's blueprint from Google is on the right track. Show them a bunch of scenarios, let them predict the outcomes, and eventually they'll learn the underlying principles.
I still think we need a more principled approach. Brute force deep learning is not going to cut it. We need to incorporate symbolic reasoning so that the AI can actually understand what it's doing and explain its decisions. Neuro-symbolic architectures offer a promising path.
I agree. We need to move beyond just pattern recognition and develop algorithms that can truly understand the underlying structure of the world. And that requires a way to translate between different coordinate representations. Maybe we need to look at how the brain does it, how it represents space and time, and try to mimic those mechanisms in our AI models.
Absolutely. And I think that's where understanding the role of language comes in as well. Language allows us to abstract away from the specific details of a situation and reason about it in a more general way. If we can combine language models with neuro-inspired algorithms, we might be able to create AI that can truly understand and reason about the world, potentially even theoretical concepts in physics.
That's an interesting idea. Using language as a bridge between neural networks and symbolic reasoning. I wonder if we could train a language model to generate symbolic representations of physical systems. Then, we could use those symbolic representations to reason about the system.
Yes, and the nice thing about symbolic representations is that they're explainable. You can actually see the steps the AI is taking to arrive at a conclusion. That's a huge advantage over deep learning, where it's often a black box.
It's also important to consider the temporal aspect. Current models are largely static. How do we create a dynamic representation of time that allows the model to reason about past, present, and future? Deep learning seems to struggle with these nuanced mappings.
Okay, so let's drill down a bit. What are some specific research directions we could pursue in this area? What are the low-hanging fruits, and what are the grand challenges?
From a deep learning perspective, I think we need to focus on developing better architectures for spatiotemporal reasoning. Things like recurrent neural networks and transformers are a good start, but we need to go beyond that. We need architectures that can explicitly model the relationships between objects in space and time.
I think we need to focus on developing more robust neuro-symbolic architectures. We need to find ways to seamlessly integrate neural networks and symbolic reasoning so that we can get the best of both worlds. A system that could use a neural network to identify objects in an image, and then use symbolic reasoning to determine the relationships between those objects. This is way more useful than just brute force deep learning that doesn't know why things are behaving how they do.
I think we need to focus on developing algorithms that can translate between different coordinate representations. This is a fundamental problem that needs to be solved if we want to build AI that can truly understand the world. So, how do we encode spatial, temporal, and even abstract coordinate systems? How can a system translate effectively between them? My hunch is that a capability like this is a major roadblock to AGI, and that current deep learning struggles with these nuanced mappings.
From my perspective, I think we need to draw more inspiration from the brain. We need to study how the brain represents space and time, how it integrates information from different senses, and how it uses language to reason about the world. And then we need to try to mimic those mechanisms in our AI models. Perhaps language models can be trained on theoretical physics papers to generate AI architectures that mirror the brain processes in physics, rather than purely relying on statistical methods.
Okay, so architectures for deep learning, better neuro-symbolic integration, coordinate transformations, and brain-inspired algorithms. Sounds like a good roadmap for future research.
Yes, and we need to be careful not to get too caught up in the hype around deep learning. We need to remember that it's just one tool in the toolbox and that there are other approaches that may be more promising in the long run. The key is to create an architecture that can think and adapt on its own to theoretical problems.
Agreed. We need to be open to new ideas and new approaches. The current paradigm might not be the right one, and we need to be willing to challenge our assumptions and explore alternative paths.
Absolutely. And I think that's what makes this field so exciting. We're on the cusp of something truly revolutionary, but we're not quite there yet. There are still many challenges to overcome, but I'm confident that we'll get there eventually, maybe with the help of language models that can analyze theoretical physics and even generate new hypotheses or predictions. Perhaps that can accelerate the translation of neuroscientific insights into computational models.
Definitely. I see a future where AI can help us solve some of the biggest problems facing humanity. It's not just about building smarter machines, it's about building machines that can help us understand ourselves and the world around us.
I agree. AI has the potential to transform society in profound ways, but we need to make sure that we're developing it responsibly, with a focus on explainability, transparency, and fairness.
Right, and with a focus on spatiotemporal reasoning. We can't forget that the world is dynamic, and that intelligence requires the ability to reason about relationships in space and time. Current deep learning, while impressive, feels fundamentally static. A true spatiotemporal reasoning engine needs an inherent dynamic model.
Well, that's all the time we have for today. Thanks for joining us on Cognitive Spirals. We hope you found this discussion informative and thought-provoking. Till next time.
Thanks for having me.
It was a pleasure.
Good to be here.